Welcome to the 31st class of this open course on diffusion in multi-component solids. In this lecture, we will discuss point defects in intermetallics and ionic compounds. I have first explained the nature of B2 and L12 type of structures and then discussed various defects with respect to these structures. The defects that are discussed include Schottky defects, Frenkel defects, anticides, and triple defects. Now that we have gone through the point defects and diffusion mechanisms in metallic alloys, next couple of classes I would like to go over the point defects and diffusion mechanisms in ordered structures. Ordered structures means there is a site preference. For example, in ionic compounds or intermetallics, if you have a metallic alloy of say components A and B, there is no site preference. The alloying is random, which means B is randomly distributed in A or A is randomly distributed in B. However, in ordered structure there is a site preference. In ionic compounds, different types of ions would like to bond with each other, and in intermetallics the enthalpy of mixing is so highly negative that an order is established. Every A atom would like to have B as its neighbor, or every B atom would like to have A as its neighbor. Depending upon the stoichiometry, the type of the crystal structure will be different, and obviously it will be different from either pure A or pure B. So, first let us take a look at couple of important ordered structures. The first one of it is called a B2 structure, and the intermetallics are compounds with the stoichiometry of the form AB exhibit this type of crystal structure. So, B2 structure basically can be looked at as an interpenetration of two simple cubic sublattices, one for type A atoms and the other for type B atoms. If we draw a single cubic cell, it resembles a BCC unit cell with all the corner sides occupied by one type of atom and the body center occupied by the other type of atom. So, in this case I am denoting type A atom, which is located at the body center with this red color and the blue color on the corners are the type B atoms. So, this is B, this is E. So, each of the A and B form their own sublattices, which is of the type of simple cubic. So, in this particular cube, it is very easy to see the simple cubic sublattice of type B, because all the corner atoms are occupied by type B. In order to see the sublattice of type A atoms, if we can visualize 8 cubes placed side by side and one below the other, all the body centers are occupied by A atoms, and if you connect those, you will be able to see simple cubic unit cell of type A sublattice. So, if we can imagine one cube on the right side of this one, type A atom will be at the body center of it, one cube below this one and the one cube below the cube which was on the right side, and then you can imagine similar 4 cubes placed in front and see the body centers of those. So, this is another sublattice of type A atoms. So, you can see two interpenetrating simple cubic sublattices, and the sublattice of A at the body center of it you have a B atom, sublattice of B at the body center of which you have an A atom. So, this is the B2 type of structure. You can see in B2 structure there are 8 nearest neighbors to any atom. So, if you consider this atom A located at the body center of this cube, you can see 8 B atoms at the corners which are the nearest neighbor of A. So, all the nearest neighbors are of different type. So, 8 nearest neighbor atoms, let us denote nearest neighbor as double N, all of different types. And each atom has 6 second nearest neighbors. So, if you consider any corner atom, for example, you can see the 3 next nearest neighbor within this cube itself, and the 3 you can imagine, one on the right, one on top, and one in the cube in front. So, there are 6 second nearest neighbor, or what we call as next nearest neighbor. Let us denote it by triple N, 6 next nearest neighbor, and all of same type. So, you can see all next nearest neighbor of any B atom are B atoms, all next nearest neighbors of any A atom are A atoms. This is important, understanding next nearest neighbors and nearest neighbors, because it will help us in understanding the diffusion mechanism. For example, any jump onto the nearest neighbor site will lead to the formation of wrong bonds, whereas any jump onto the next nearest neighbor site will not cause any disorder in the system. So, we will see that later. Also, if you see, each corner atom is shared by 8 cubes. So, there is only one B atom per cube here, because there are 8 corner atoms divided by 8, and there is one A atom which is lying completely inside at the body center. So, the stoichiometry A B can be maintained by this type of arrangement in the B2 structure. Now, the ionic compounds will be mostly stoichiometric, but in intermetallics some non-stoichiometry is allowed. With that we have seen, depending upon the shape of the Gibbs free energy versus composition curve, we can have some miscibility within the intermetallic. The examples of this type of crystal structure, you can see nickel aluminide NiAl or iron aluminide FeL, they have B2 type of structure. Both of them show a wide solubility range on both sides of the stoichiometry. Then CsCl is an ionic compound which shows this B2 type of structure. Another important crystal structure in ordered compounds is called as L12 structure, and this occurs in compounds of the stoichiometry A3B, 3 atoms of A per atom of B, and this L12 structure can be simplistically looked upon as a face center cube with all B atoms at the corner and all A atoms at the face centers. So, all B atoms the corners, all A atoms, the face centers. So, this is A type of atom, and the blue circles are B atoms. So, you can see each atom in this structure has 12 nearest neighbors. If you consider any A type of atom, for example, out of the 12 nearest neighbors, 4 are of different types and the remaining 8 are of the same type. That is, 8 nearest neighbors of any A atom are type A atoms and 4 are B atoms. Right. So, 12 nearest neighbors for A, 8 of the type A and 4 of the type B. Whereas, for B you can visualize any B atom, all 12 nearest neighbor for any B atom are A atoms. Since each face is shared by 2 cubes and there are 6 faces, so there are total 3 atoms per cube here of type A, and each corner again is shared by 8 cubes. So, there is only 1 B atom per cube. So, the stoichiometry of A3B type is maintained by this type of structure. Now, if you look at the next nearest neighbors, again there are 6 next nearest neighbors for any atom. So, we have 6 next nearest neighbors and all of them you can see are of the same type. Okay. The example of this type of crystal structure is Ni3L. It has the stoichiometry of the type A3B, 3 nickel atom and 1 aluminum atom per unit cube. So, this is the L12 type of structure. Now, let us take a look at some of the point defects that occur in ordered structures. In metallic alloys, there is a metallic bond, which means the positively charged ions are floating in the sea of free electrons. Formation of a vacant site or addition of an impurity does not cause any disturbance of the charge neutrality. However, in ordered structure, as you can see, if you leave one site vacant, it leads to disorder in the structure. In ionic compounds, it will cause a local disturbance of the charge neutrality. And so, the defects in ordered structures most commonly occur in pairs. For example, in an ionic compound, if there is a cation vacancy, then it will be negatively charged, because a cation has a positive charge and a missing positive charge, the vacancy has a negative charge. So, to balance this extra negative charge, one anion vacancy is created, which has a positive charge, and this pair of vacancies on anionic and cationic sites is one type of defect, which is called as Schottky defect. So, it is a in case of ionic compounds, anion vacancy and cation vacancy. So, if you consider an ordered structure, so the red atoms are type A, so blue atoms are type A, the red atoms are type B. Let us denote a vacancy by a square. So, if we create a vacancy on B sublattice, this maintain the charge neutrality, a vacancy will be created on an A sublattice. Okay. So, this is denoted as V A, vacancy on A sublattice, and this is V B, vacancy on B sublattice, and this is the Schottky defect. So, for Schottky defect, you can see the equilibrium concentration of one type of vacancy should be equal to the equilibrium concentration of the other type of vacancy. Now, if the size difference between A and B is large, then the smaller atom can actually occupy an interstitial position. So, once the vacancy is formed by a smaller atom, instead of the bigger atom forming a vacancy, the atom will A will go and sit into the interstitial site. So, in an ionic compound, the smaller ion can fit into the interstices. So, the energy required to form the anion vacancy may be larger than the energy required to form a cation interstitial, and so a cation interstitial will accompany a cationic vacancy. The cations are usually small, and so you will see cation interstitial and cation vacancy pairs, and this is called a Frenkel defect. P type of atom, and an A atom, an A atom leaving its site will leave a vacancy behind, and A being very small can occupy an interstitial site. So, this is we call A I, interstitial of A, and this is V A, the vacancy on A sublattice. So, this is the Frenkel defect. So, for Frenkel defect, the equilibrium concentration of cation interstitial should be equal to the equilibrium concentration of cationic vacancy. Now, depending upon the charge difference and the energy required to form anionic vacancy, you can have a mixture of cation vacancies, anion vacancies, and the cation interstitials. Next type of defect is called an anti-site. As the name suggests, it is an atom occupying site on a wrong sublattice. So, B atom occupying an A sublattice site or an A atom occupying a B sublattice site is called an anti-site. So, here you can see this is an A atom which is wrongly placed on a B sublattice. So, this is an anti-site of A on B, we denote it as A B. If we have a B atom occupying an A sublattice, like here, this is called anti-site of B on A, it is denoted as B subscript A. As you can imagine, if the atom size is small, like an A atom here, the size of A atom is much smaller than that of B atom, then forming an anti-site of A does not require much energy. But since B atom is very large, forming an anti-site of B on A requires large amount of energy. So, typically you will see considerable equilibrium fraction of anti-site of smaller atoms, and this will be especially important when there is a non-stoichiometry. For example, in NiL, nickel atom is smaller and aluminum is larger. So, if we have nickel rich NiL, that is, if nickel aluminide is of stoichiometry and has larger amount of nickel than 50 mole %, then it will be accommodated by formation of nickel antisites. However, on the aluminum rich site, the formation of aluminum antisite is a very high energy event. So, the equilibrium concentration of aluminum antisite will be much lower. So, the extra aluminum, that is the off stoichiometric aluminum, will be accommodated by formation of nickel vacancies. In ionic compounds, the antisite formation is very rare, because there is an ionic bond between A and B, and so forming an antisite leads to formation of wrong bonds, again which is a very high energy structure. So, the antisite in ionic compounds will almost not be possible. Then the next defect is called triple defect. As the name suggests, it is a defect complex involving 3 defects. So, there are 2 vacancies involved and 1 antisite. So, it is a combination of, for example, here one antisite of A on B sublattice and 2 vacancies on A sublattice. So, this is a triple defect. So, this is an important defect that can assist in diffusion of A and B, particularly A, because A being smaller forms an antisite. So, we will see that later, how it assists the diffusion. So, in case of B2 structure, to visualize this defect, So, I have shown 2 unit cubes of B2 structure, one above the other. You can see there is one A atom which is occupying the B sublattice, and the 2 body center sides which are supposed to be occupied by A atoms are vacant. So, the 2 vacancies on A sublattice and one A anti-site. This is how the triple defect would look like in a B2 structure. Okay. So, these are some of the important defects which occur in ordered structures. In the next class, we will go over the diffusion mechanisms in these ordered structures. Thank you.